first. Then let's start today's seminar. Today's speaker is Philip Liu from SNU. He will talk about PBH cloud cooling bonds and high temperature QCD PBH formation. Please start when you're ready.
Yeah. Hi. So today there will be two parts to my talk. In the first half, I will talk about a set of cooling bounds and heating bounds on the PBH mass density. And in the second part, I will talk about a PBH formation scenario within a high temperature QCD setting.
Screen.
Yeah. So first, why primordial black holes? Well, primordial black holes have a lot of interesting properties, and also there's some possible signals of their existence. So first, there's an open mass window where primordial black holes can be a viable dark matter candidate. So this is between 10 to negative 16 to 10 to negative 11 solar masses. So asteroid mass primordial black holes. Second, there are macroscopic dark matter candidates. There's a few macroscopic dark matter candidates like Q balls or PBH, but PBH are by far more popular. And they have much more interesting phenomenology and much different phenomenology than particle dark matter candidates like WIMPs. They often are associated with gravitational waves, right? If you form them through the usual horizon overdensity collapse process, then you get gravitational waves from the curvature power spectrum. And if you form them through first order phase transitions, then you also get gravitational waves from bubble wall collisions. So PBHs and gravitational waves are usually tied together. Finally, they can also see supermassive black holes. So as we know, there are supermassive black holes at the center of most galaxies. And we know from AGN observations that some of these supermassive black holes were actually formed quite early in our universe. So a recent JWST observation suggests that there may be a supermassive black hole at a redshift of 10.6. So of course, these could be formed through some astrophysical process, but it does put a lot of strain on models that don't involve some sort of massive PBH seeding these supermassive black holes. Finally, for signals from our binary merger populations, we know that there's maybe too much black holes within this supposed mass gap between 50 to about 100 solar masses. So it's hard to directly form stellar black holes within this mass gap, but maybe there's some process of merging or accretion. But naturally, people have suggested that some of these black holes may actually be primordial in nature. And there's also microlensing candidate events from OGLE and HSC. And both of these have possible detections of a PBH lensing. So for the first part of my talk, this will be cloud cooling and heating bounds. So first we look at this well-known plot of many PBH bounds. On the very left-hand side, we have the bounds from our Hawking radiation. So all these bounds in red come in some way or another from light PBHs evaporating very quickly and emitting a lot of high energy particles. In the next region, just a bit higher mass, we have three bounds shown in dashed lines. So these bounds were found to be unreliable. So therefore, this is the open mass window where PBHs can comprise all of dark matter with basically no issues. To the right, we have a few bounds, some of which are from microlensing. In particular, HSC and OGLE are two microlensing experiments that have possible detections of PBH. And finally, the last region that I want to focus on today is this intermediate mass black hole range from about 10 to 10 to the 5 solar masses. So within this intermediate mass range, we see that we have a few very strong bounds. For instance, XR, XP, and PA, the Planck CMB bound, are all accretion disk bounds. In particular, the Planck bound is the strongest by far, and it depends on accretion during the CMB era. So you need a lot of PBHs during that era, and it will mess up your CMB spectrum. So the first bound we're going to be talking about today is also an accretion disk bound within this range. But instead of the Planck bound being a cosmology dependent bound, R bound is based on present day observations and present day data. Why this matters is actually in a recent paper, my co-authors and I have shown that you can create PBHs very late in the universe after CMB eras, which in that case, the Planck bound, for instance, would not apply. So just overall, how does this PBH constraint be imposed? Well, first, we assume that there's thermal equilibrium. So we find a very stable gas cloud that's very long-lived. So the heating rate should be equal to the cooling rate, more or less, right? And we actually ignore all the heating from our standard sources like stars. This actually makes our bound more conservative because if we were to estimate all the normal astrophysical heating processes, that would actually leave less room for PBHs and a stronger bound. But of course, there's too much uncertainty, so we just ignore those. This type of argument was actually first applied to particle dark matter by these authors, Buna et al. And also Waker and Farrar, who improved upon their method. And they talked about local heating, how much heating you have in a local space versus how much heating you have in a local space. But when we have primordial black holes, well, they're macroscopic objects. So being macroscopic objects, we care about how much total heating and how much total cooling you have within your entire gas cloud. So by requiring thermal equilibrium, we get a bound on the PBH mass density. So naturally, if your cooling rate is higher within the gas cloud, this leaves more room for all types of PBH stuff to go on. So that makes your bound weaker. And if your heating rate for each PBH is higher, that actually makes your constraint stronger. Finally, yes.
I think many people here are not familiar with the black hole. So
okay, yeah.
could you explain a little bit what is the underlying mechanism for heating and cooling?
Great, yeah.
Very, very elementary question, but
no, I mean that was a good question. Yeah, so in this talk, the heating will come from mostly accretion disk physics. So when you have a black hole in gas and dust, it accretes material, and then you emit radiation like photons from the accretion disk. So this photon will go on to heat up your cloud. Another possible source that I talk about is Hawking evaporation. So for very light PBHs, the Hawking evaporation, you can either detect it directly, but some of it is absorbed by the gas and dust. So that also heats up. So yeah, heat.
I mean, Hawking radiation is included in the heating rate or cooling rate?
In the heating rate.
The heating rate.
Yeah, in the heating rate of the gas. Yeah. And
Okay.
yeah.
Heating of the gas.
Yes, heating of the gas. Yeah.
So what's the mass range when you are considering this heating process?
Right. So pretty much there's two mass ranges for this constraint. The first one is the intermediate mass black hole range. So PBH around 10 to 10 to the 5 solar masses actually form accretion disk quite efficiently. For Hawking evaporation between 10 to the 15 grams to 10 to the 17 grams, you get significant amounts of radiation. So yeah. So depending on the mass range, the heating process changes. Yeah. Great. Yeah, good question. So there's also a lower bound on this constraint. And this lower bound basically just says that within your gas cloud, you need at least one PBH. For instance, in the next slide, we're going to be talking about our main system, which is LEO-T. This is a dwarf galaxy. And within this dwarf galaxy, there's about 10 to the 7 solar masses worth of dark matter. So that also means that we can't give any constraint on PBHs that are more massive than 10 to the 7 solar masses. All right, so LEO-T is a really good candidate actually because it's been well studied and modeled in the previous papers. It's also relatively dark matter dense and gas dense, and actually has so much gas that it seems to be right below the cusp of significant star formation. But because it actually does not have a lot of star formation, this makes our gas more stable. There's less going on. It's easier to calculate the cooling rate and also the heating rate. Finally, there's no coherent detection within coherent rotation within the OT. And this matters because when we have accretion, and you have a PBH within the gas cloud, the slower the PBH moves relative to the gas, the more it accretes and the better accretion disk forms. So the slower things are moving, the more heating you get overall. So LEOT is actually quite an ideal candidate. And we focus on the inner 350 parsecs or so because the gas here is unionized. And when you have unionized hydrogen gas, your cooling rate is very small. Now, so in the unionized hydrogen gas, the cooling rate is dominated not by the hydrogen itself, but by the metals inside the hydrogen gas. So you see, for example, that oxygen or carbon are big contributors to your cooling rate. Now, this is a collisional cooling rate. So it happens whenever you have two particles that scatter. So therefore, your cooling rate is proportional to n squared for the collision rate. It's also proportional to your metallicity, right? How much oxygen, how much carbon you have. And there's a slight dependence on the temperature. Now, plugging all these factors in, you find that for LEOT, your cooling rate is actually quite low at 10 to the negative 30 ergs per cubic centimeter per second. So
is this numerical calculation?
Yeah, I think this is a numerical calculation that these two papers did.
Oh.
Yeah, it's really hard to calculate that from first principles. Yeah, so for heating processes, right, that's one half of the story, the cooling processes. For heating processes, we have three. And the first one is the accretion disk itself. So you have a massive black hole, you have the interstellar medium, and it accretes and forms an accretion disk, which we model using Bondi-Hoyle accretion. And it forms either an ADAF disk, which is a very thick, kind of dispersed disk with a lot of turbulence. And this is for low accretion rates. But for high accretion rates, we get a more classic thin disk. So what you might imagine when you think about an accretion disk. Now, these are very efficient at converting gravitational potential or energy into radiation. Finally, we not only care about how much radiation you produce, but how well that radiation is absorbed by the surrounding gas. So we have to impose an extra optical depth factor, right? It's not just about how much photons there are, but how many of these photons are producing heat. And this optical depth factor is actually quite bad for LEOT, something around 10 to negative 3 or 10 to negative 4 factors imposed. So for our second process, it's also from the accretion disk, but these are high energy protons that come from these turbulent winds that form when you have an ADAF thick disk solution. So the winds themselves are very high energy protons, which can then scatter with the surrounding gas and dust and give them heat. Right. So the first process is just the radiation, the photon radiation from the disk. The second is kind of the outflows from the disk. And finally, the third process is dynamical friction. This is a direct heating process that happens whenever you have a macroscopic object moving within a bunch of lighter gas and dust. And this can actually be directly computed, but unfortunately, it turns out that it's always a subdominant process.
What is the y-axis in the last?
Right. Right. So the y-axis is the gas density, and the x was the PBH mass. So basically, as you increase the gas density or the PBH mass, your accretion rate increases. So for different values of your accretion rate, you get different types of solutions. For instance, for low accretion rates, you get ADAF or this VADAF, which is even weaker. And for higher accretion rates, you get something like a thin disk, which produces a lot of UV radiation.
So the location of the black hole is an important thing, or location is always at the center of the galaxy?
Yeah, so we're just talking about the central region, and the location could be anywhere within the central region. From the previous slide, the hydrogen density does change, but we just assume a constant value somewhere in the middle, right? So basically, the accretion rate depends on your PBH mass, and this determines what kind of disk you form. Yeah. So for low accretion rates is the ADAF solution, advection-dominated accretion flow. Again, a lot of turbulence and a lot of different processes for producing radiation. You see that the spectrum actually peaks within the synchrotron range, And this is for radio frequencies. However, remember, we have to take into account how well this radiation is absorbed by the gas. So it's actually the inverse Compton and the Bergstrom components that are most readily absorbed because they're ionizing radiation, right? It's a hydrogen-dominated gas, so ionizing radiation is much more powerful than radio frequencies. Finally, for high accretion rates, we form a thin disk, which is basically a series of black body radiation at different temperatures along the disk. Now, it's a much higher emission rate for photons, and the peak of the emission is actually within tens of eV. So that's well within the ionizing radiation range. So whenever we have massive enough PBH to form thin disk, we get a lot of heating and we get very strong constraints. Our second component, again, is winds. And we model this using a power law inflow-outflow model. But unfortunately, there's actually quite a lot of debate within the winds literature about how strong these winds really are. So we've taken both the weakest parameters and also the strongest parameters. So we have a low wind and high wind model. So you see that there's actually a big difference in our constraints depending on the strength of the winds themselves. And finally, our third heating process is dynamical friction. And this can be analytically calculated. You see from the graph that dynamical friction actually has a resonance behavior. When the velocity of your PBH is the same as the sound speed of your gas, there's a resonance and you heat up the gas much more strongly. So this is actually true for our VOT PBH. But even with this resonant behavior, we still get very, very weak heating contributions. So the main heating contribution is from our photons in the accretion disk themselves. So the two graphs, the one on the left shows you the heating rate from each contribution taken separately. The red is our accretion disk luminosity. So you see that it increases steadily. And the blue is this very uncertain wind contribution. So there's a range of parameters for the low wind model on the bottom and for the high wind model on the top. So if we assume very strong winds, taking the most optimistic parameters we could find, the winds dominate your heating and they also dominate your constraint. However, if we take very unfavorable values, then your constraint and your heating comes solely from your accretion disk photons. Finally, the green is the dynamical friction, which is always subdominant. And the graph on the right shows you what kind of constraints you will get from each of these heating processes. So in the low wind model, you have a constraint just from your photons. In the high wind models, your high energy protons give you a very strong constraint. So this is the constraint plotted against all the other constraints in the relevant region. You see that it's quite competitive compared to some of the other accretion disk bounds. The Planck bound here is of course stronger, but it could be avoided if you made very late forming PBH.
Sorry,
Yes.
maybe I'm confusing. So this is, I mean, which observation is related to this phenomenon?
Oh, which observation? Well,
Yeah.
it'd be observations of LEOT. So given your gas density and also dark matter density, you can then calculate your cooling rate.
Okay.
So that says kind of how much heating you can get away with, right? The heating rate itself you can calculate just from PBH, black hole accretion disk physics. Yeah, so this sets how much heating you can have. And overall, when you compare the heating rate and the cooling rate, you end up getting a bound. So it's observations of the temperature of LEOT and how much gas there is, which implies how much cooling there is.
Temperature of the gas.
Yeah, temperature of the hydrogen gas in LEOT.
What is the kind of name of the observation? Experiments, kind of.
Oh, I'm not sure exactly which experiments we got this from,
Mhm.
but just any generic telescope, you look at BOT, you can kind of infer how much gas there is and so on.
Oh, thank you.
So here you are requiring that the temperature of this LOT is constant.
Yes,
Right.
yeah, we're requiring that as constant, and we have relatively good reasons to assume so because there doesn't seem to be too much going on within the OT. If there was a lot of star formations, a lot of supernovae going on and all that, then of course the temperature will fluctuate. But it seems to be a relatively quiet system. So yeah.
So this assumption is based on the observation or any other physical principle.
Yeah. It's based off the fact that there seems to be nothing that should be changing the temperatures. Yeah. Great. So this is our original constraint. And then we consider what the effects of having a PBH spin would be.
One more silly
Yes.
question.
No,
So
go ahead.
if you look a different, for example, target, then you can get different bound.
Yes, exactly.
Oh,
So, for example, for particle dark matter, they consider both VOT, a dwarf galaxy, and also they consider these Milky Way gas clouds. Now, the reason why we don't want the Milky Way gas clouds for PBH is it turns out we get much less accretion. And when we get much less accretion, way back to his question, we get different accretion disks that are much less efficient. So overall, the best target for this type of analysis is actually the OT.
nice.
Yes. Yeah, so when we take in the effects of spin on this heating rate, we find that spin decreases your innermost stable circular orbit, your ISCO radius. So that basically means that you can bring in your accretion disk closer to the PBH, which of course means that you convert more of the gravitational potential energy into radiation. So that's the first effect, and that actually has a secondary effect of increasing the energy in your accretion disk. So you increase the plasma temperature, which leads to much more Bremsstrahlung and much more inverse Compton radiation than before. Second, sometimes when you have spinning PBH, you can form jets. Right? We're not exactly sure how often these jets form, but we do know that jets are possible. So you can have Blandford-Zenag jets, and when you have such jets, your efficiency of converting your accreted material to luminosity could actually be very high, could actually be 1. Actually, in some cases, you can have an efficiency factor greater than 1. That's when you start converting some of the angular momentum into energy. So for models of magnetically arrested disk, we get efficiency factors of 1. However, if we look at models of quasar outflows, the efficiency factor might be something like 5 times 10 to the -3. So again, there's still a lot of uncertainty involved with this jet phenomenon. So we've taken actually both of these values. And there's also additional factors that you can impose. For example, duty cycles, how often these jets are turned on or off, and also the heating efficiency. So for these jets, we actually get much more efficient heating than previously, because when you have jets forming a powerful shock front, the shock front is optically thick to the jet particles. So much of the energy actually gets absorbed by the shock front, which disperses into the surrounding gas and dust. So we've also included an extra factor of 1/2 to include duty cycle and heating efficiency phenomenon. And if we include these spinning PBH, our original non-spinning bound is shown in blue. Our spinning PBH, just from decreasing the ISCO radius and having more conversion of that gravitational potential energy, that's shown in black. And the additional jet contribution, if jets are ubiquitous, is shown by these double lines of low efficiency, the value suggested by quasar outflows, and high efficiency, the value suggested by MAD simulations. Of course, we don't expect jets to form for every PBH, so the true bound will be somewhere between, somewhere in this region, depending on exactly what fraction of PBHs form jets and what type of jets they form. But yeah.
How much angular momentum? So did you assume?
Right. So for this, I think it's a 0.9 spin. 1 being maximal, 0 being non-spinning. Yeah. So quite high, but not extreme. Yeah. Yeah, finally, there's an application of this type of process to evaporating PBH. So for intermediate mass, 10 solar mass, 100 solar mass PBH, they're very good at forming accretion disks. For very light PBH, you don't really form an accretion disk, but you can go through Hawking radiation and Hawking evaporation. And this leads you to set bounds somewhere around in this region of 10 to negative 17 to 10 to negative 16 solar masses. Now, we originally just wanted to include the effects of spin because there's already a paper out on this cloud cooling process applied to evaporating PBHs. But when we reanalyzed the non-spinning bound, we found that we had orders of magnitude difference, right? So this is that paper's graph, which shows that this cloud cooling bound is actually the strongest over some of the mass range. But this does assume that all your positrons and electrons that you emit from your Hawking radiation are trapped within the OT, that they pretty much are magnetically trapped and they circle around until they deliver all their energy into the gas. When we redid this, but without this assumption, we found a much, much weaker bound. So just briefly on Hawking evaporation, you get a black body-like spectrum from Hawking radiation. So it also depends on your angular momentum. So when you have spinning PBH, you get more emission of higher angular momentum particles. So more photons compared to neutrinos, for instance. The temperature of your PBH depends on inversely actually with your PBH mass. And it actually decreases with increasing spin. But the overall effect of having a spinning PBH is that you get more emission and more heating. So taking all this into account, the black line is the bound for non-spinning PBH. Instead of being the strongest bound within this range, it actually is one of the weakest, but there's still a bound. Now, of course, there should be some particle trapping, right? So the true bound, if we're able to analyze the exact amount of particle trapping, would be somewhere between our bound and the original bound shown. The dashed line shows that if you do include spinning PBH, you do get a stronger constraint because you get more emission. Okay. So to conclude, we require thermal equilibrium within this dwarf galaxy DOT, which we assume to be stable because it seems to not have much star formation or supernova going on. This bound is cosmology independent, which again is important because we also came up with a model of late forming PBHs that can evade bounds like the Planck bound. Whenever you add in spin, you include the possibilities of jets. So jets, if they occur often, they'll provide a very strong bound. And finally, for evaporating light PBH, if we don't assume particle trapping, we reanalyzed the bound and found that it was much weaker than previously claimed.
So before you change the topic, so you are primary black hole the surrounding gas system, and you are assuming this whole system is in thermal equilibrium?
Yes, in the long run, over timescales of probably 100 million years or so.
So black hole eat up the surrounding gases, etc., and also black body Hawking radiation.
Well, if they form the accretion disk, then it's not Hawking radiation. It's just from the accretion disk itself will have, maybe black body.
So
Yeah.
from the accretion, you emitted photons.
Yeah, photons. Yes.
That will heat up.
That will heat up. Yeah.
Um,
So this is kind of like a continuous process. For example, we know that there's like X-ray binaries and stuff like that, right? And those are black holes that have accretion disks that emit stuff. So this is a continuous heating process compared to a continuous cooling process.
So Hawking radiation is not very important.
Oh, well, it is, but Hawking radiation is important for the light PBH. So when you're around 10 to the 17 grams or so, then you get a lot of Hawking radiation. But when you're talking about 10 solar mass or 1,000 solar mass black holes, the Hawking temperature is inversely proportional to your mass. So those emit sub-radio frequencies of Hawking radiation. They're negligible.
Okay, so I was wondering how, I mean, this assumption of thermal equilibrium is a good enough reasonable assumption.
Yeah, I think we made some estimate of what time scale you would need. And if you're in thermal equilibrium over about 100 million years or so, then it's good enough. And I forget the exact papers, but I think you could kind of tell the star formation rate from the number of new stars and so on. And it's been low enough where, if you have a starburst galaxy, then probably not in thermal equilibrium. If you have a very quiet dwarf galaxy, then thermal equilibrium is more reasonable. Yeah, so the thermal equilibrium arguments or the estimates were actually made by the authors of Wade, Carr, and Farrar. So the original paper on this type of cloud cooling process, they made a mistake in that they used some very unstable gas clouds. If they're unstable, then you definitely can require thermal equilibrium. But they reanalyzed it and they said, okay, those are unstable for these reasons. But here are a few stable, very stable gas clouds, which have timescales long enough to assume thermal equilibrium.
Do you know this first name of Kim here?
Yes, Hyungjin.
Hmm?
Hyungjin Kim. I think I've seen him give some talks in Korea. Yeah. So yeah, for the second part of my talk, I will talk about PBH formation scenario in a high temperature QCD transition. So of course, a high temperature QCD transition will be a non-standard model, right? So why should we even consider such a transition? Well, from lattice QCD simulations, we know that the standard model QCD transition is a crossover transition. And it's not a first order phase transition. And first order phase transitions have much more interesting physics involved. So in order to have a first order phase transition, you need 3 or more massless quarks. So this comes about naturally when you have a higher temperature QCD transition, because the masses of your quarks are effectively massless compared to the scale of your transition itself. So depending on whether you're above or below the electroweak scale, you have 5 or 6 massless quarks. So you have a strongly first order phase transition. So there's a few models going around of such a high temperature QCD transition. We talked about one in our paper by Ipek and Tate because it's particularly simple, where they have an extra scalar that's coupled to your gluons. So the scalar acts as an extra coupling, right? Now, if your scalar gets a negative BEV, negative vacuum expectation value, it actually partially cancels the first term in your parentheses. And this is 1 over the coupling strength. So you have a strong coupling. Your coupling between gluons becomes stronger, which means that when you start to run your coupling, you asymptote much earlier, and you hit confinement at a higher temperature. So your confinement transition actually happens at an exponentially higher temperature in this model. Now, of course, you will have to restore your standard model QCD before Big Bang nucleosynthesis. And there's actually a few that they suggest. But in any case, again, there are a few high temperature QCD transition models, and this is just one of them. So to model this QCD transition, we use the PNJL model, which is an effective description of your QCD transition. Now, this PNJL model consists of your Polyakov loop, which describes your gluon sector and how your confinement happens. And you add that to an NJL sector, a Nambu-Jonah-Lucinio sector, and that describes your chiral condensate and your chiral phase transition. So it's a 2-part transition, but because we have a much higher temperature for our confinement, this actually exponentially increases the temperature of our chiral phase transition. And this is the transition that is actually first order. So again, high temperatures means that we have 5 to 6 massless quarks, which means that we have a first order phase transition. So why does it actually matter for PBH formation what type of phase transition you have? Well, you soften the equation of state whenever you have the first order phase transition. This just means that your pressure force is decreased during the transition. So let's say that normally you have a horizon size over density, and this starts to collapse into PBH. You increase the radiation energy density within your horizon, and you also increase the radiation pressure because radiation pressure is just 1/3 of your radiation density. However, during the first order phase transition, you have a low energy true vacuum and a high energy false vacuum. So when you increase the energy density within your horizon, some of that energy density actually goes into going from your low energy vacuum to your high energy vacuum. So instead of increasing your radiation density and radiation pressure, you change the phase during the collapse. So this just really results in less restoring force and less pressure that inhibits your collapse into PBH. So the effect of this on your pressure force, 1/3 being your radiation value, is that you get a dip in your pressure during the first order phase transition. The black is what we generated from our PNGL model. We've also included some other shapes to show that our results are robust and independent of the exact transition. So more quantitatively, when you decrease your pressure, it decreases the threshold that you need to collapse into PBH. So the fraction of horizons that collapse into PBH, this beta parameter, is pretty much the probability that your fluctuations have a higher fluctuation than the critical delta C. And from numerical simulations of PBH collapse, we know that this critical overdensity depends on your pressure force. As you might expect, if you had 0 pressure force, you would also have a delta C of 0. Because if there's no restoring force to your collapse, any overdensity would eventually collapse. So a nice part about this type of PBH formation compared to what you would normally do. So what you would normally do is you want a peak in your curvature power spectrum. So you induce some sort of ultra slow roll phase or some other way to induce this curvature peak. In our case, we assume a flat inflationary power spectrum, which is much easier to accomplish. And our peak in our PBH production comes from this weakening of pressure forces during the transition.
What is the alpha there?
Alpha. Delta? Oh, alpha? Oh, alpha, I think, depends on the shape. So there's a weak dependence on exactly how your pressure dips because, it's not an instantaneous collapse. It takes some time to collapse. But the conclusion from the alpha is that there is some slight dependence. But you see that it's quite weak. Generally, when you decrease your pressure, you increase your production. I think we assumed an alpha of 1. Yeah, so the density of PBHs that you get, as you might expect, is just directly proportional to the fractions of horizons that collapse, right? And as you see, we've produced a distribution of PBH within the PBH mass window where it can be all of dark matter. Now, our results are pretty robust in that it doesn't really matter the exact shape of our power spectrum, of our equation of state, we still get pretty much PBH dark matter, even if our results are, our PNGL model is not directly applicable. So another property of a high temperature QCD transition is that when you form PBHs, the PBH mass depends on the horizon mass during your collapse. So if you had a standard model QCD transition at 200 MeV, the PBH mass that you get is about 1 solar mass, which is not the most interesting space because just a few solar masses, you can have stellar black holes, right? So if you had PBHs of a few solar masses, you can't tell the difference.
So in this case, the
Yeah.
peak comes from the weakening, the
Yes.
equation of state.
Yeah, yeah.
right?
So this peak comes, yeah, only from the weakening of the equatorial state. There's no
So
peak. Yeah,
this does not correspond to the peak of spectra,
that's right.
right?
Yeah.
Okay.
We just have a flat power spectrum, which is of course much simpler and much easier to get. Yeah. And yeah, so if you change the temperature of your transition, you get smaller and smaller horizons, so you get lighter and lighter PBH. So that's why we can create PBH within the dark matter mass window by assuming a high temperature transition at maybe TeV scale. So there's 3 target populations that we want to hit with this kind of PBH formation. The first one, of course, is the dark matter mass window that I already showed. The second and third are these microlensing experiments. So OGLE have 6 candidate detections, which may be possible detections of PBH. And HSC has 1 candidate detection shown below. So of course, you have some microlensing event, but you're not exactly sure what the object behind it is. So we've generated PBH with all three of these populations by varying our transition temperature. So A is our dark matter mass window, B is our HSC population, and C is our OGLE population. Finally, there's a coincidence signal when you have this PBH formation, and that's gravitational waves. So there's actually 2 sources of gravitational waves, but we ignore the contribution from the first order phase transition. So when you have first order phase transition and bubble wall collisions, you will produce gravitational waves that way, but those depend very sensitively on your parameters. We just calculate the gravitational waves from our induced, second order induced ones from our power spectrum. And the target space that we want to hit is that in the nanograph 12.5 year data, this is a pulsar timing data, there seems to be a possible gravitational wave background signal. There's some parts of it that don't exactly match a gravitational wave background, but it's a possible signal of a gravitational wave background. So that's shown by this green region right here. And we see that all 3 of our models, for instance, the model that produces PBH within the dark matter mass window, or the models that hit our microlensing experiments, also generate gravitational waves within this nanograph 12.5 year data window of this possible GW background. So it's very interesting that, for instance, we can have dark matter and also satisfy a possible signal as well. So to conclude, we consider a high temperature QCD transition because it's a first order transition when you're a high temperature transition. And the first order phase transition enhances PBH production by decreasing your pressure forces. There's also a secondary effect in that when you go to higher temperatures, your horizon mass decreases and you can get much lighter PBHs rather than just 1 solar mass PBHs. Finally, we matched our populations that produce dark matter or match the microlensing experiments. We can also generate a gravitational wave background that fits the nanograph possible signal and could also be detected by upcoming experiments like SKA, which is currently being built, or of course stuff like LISA will be able to detect such gravitational waves. Thanks for listening to my talk.
Thank you very much for the nice talk. Any question?
Could you again explain how to get high temperature QCD
Right.
in the simple example?
Right. So in this simple example,
So you add the interaction
right,
I and G,
right,
and I guess if pi gets big,
Mhm.
so it effectively change the coupling, right?
right.
And it change the running.
Yes.
So that's why you can get the high scale blow up.
Yeah.
Okay, that's the idea.
Yeah, that's correct. So if you assume something like a positive EV, then that actually makes your coupling weaker and you get a lower temperature QCD transition. If you get a negative EV, it makes your coupling stronger and you get a higher temperature QCD transition.
So in the present universe, so the wave of phi is 0.
Right. So there's a few ways to restore it, right? And that's one of the ways. So one of the ways to restore is to assume that at high temperatures, you have a negative VEV. And at low temperatures, because of the shape of the potential, your VEV runs back to 0 and you restore QCD. And you want to definitely do this before BBN and all your, your deuteron ratios are set and so on. So that's one way. Another way is to actually introduce another scalar with an opposite VEV, but that requires a degree of fine tuning. So yeah, there's a few ways to restore.
So the negative wave is crucial.
Yeah, negative VEV is crucial in this
So
scenario.
if you consider phi squared, it
Yeah.
doesn't work.
No, yeah, it doesn't work. If you consider phi squared, then you can only have a positive value, which means a weaker coupling effectively. Yeah.
You show the next slide.
Yeah.
Here you.
Yeah, so the PNGL model, as far as I know, is an effective model that was used to describe QCD transition. These terms show, your quark sector, and this is your gluon potential.
So is the last sentence important for your study?
Yes, so you see that this type of coupling would just increase your confinement scale because it changes your running of the coupling, right?
So you're applying this number in your model at low temperature, not at high temperature.
Well, at high temperatures actually. So it is an extrapolation past its original intent. So yeah.
Okay, but this. My question is a little bit could be misleading, but
Yeah, that's fine.
okay, in ordinary QCD, you have a QCD and after final transition or confinement, you have mesons.
Yeah,
So,
exactly.
and it's difficult to match these two. So in the middle, people often consider kind of a toy model. I mean,
Yeah, that's correct.
to make a connection between QCD and hardware.
Yeah.
And so here,
So it's definitely an extrapolation. But yeah, basically this PNGL model connects the two, right? It connects your confinement transition that happens when you're coupling asymptotes, and then your chiral transition that happens when you get a chiral condensate, right? So basically the last sentence means that this kind of strong coupling changes your confinement scale to higher, and your higher confinement scale kind of drags your chiral transition with the chiral condensates to also higher values. And it's actually the chiral transition that is the first order transition.
and next slide.
And next slide, we show how the pressure forces changes during this transition, which you can calculate using PNGL model.
And different colors correspond to.
All right, so yeah, the different colors are actually, the black is the PNGL model. The different colors is actually related to your question, because we are taking PNGL to places where it wasn't meant to describe initially. It's possible that the PNGL results are not directly applicable. They could be, slightly different when you actually have a high temperature QCD transition. So these different colors are just arbitrary shapes that we made to show that even if this PNGL is not entirely accurate and the results are a bit different, we still get the same PBH production.
So different color correspond to different phi valve over M star? Or
Oh, no.
how, I'm wondering where this phi valve over M star appear in your study?
Oh, I see. This is like a toy model that we discussed, but there are other models. So we wanted to keep it, we want to keep our paper a bit separate from a high temperature QCD transition. Ours is more concentrated on the PBH production. So assuming you have some dynamics, it could be either 5 VEV, or it can be, there's some other models too. We only care that once you have a high temperature transition, what happens. But if you change the value of the 5 VEV, it changes your confinement scale and changes your transition scale, basically.
Any other question? Actually, I have some questions. So, could you show me the plot for hep-ph. Yeah, this one. So, how many parameters you have to adjust the
This kind of graph.
Yeah.
Yeah. So the most important parameter is the temperature of your
Yeah, so
transition.
it's peak,
It's
that
peak, yeah.
peak, right? But I mean, I wonder the F, so how to say, how big F it is.
Yes. So how big F it is also depends on your curvature power spectrum.
Yeah, so, yeah, actually, that was also my question. So you just export the current observation to the or frequency range of out the Planck data, or you use some different.
Right. So the current observations only limit your curvature power spectrum. So you don't know exactly what the amplitude is, but these are all below the current, bounds on the amplitude. Yeah. But yeah,
What do you mean bound? I mean,
so we don't know exactly how strong the curvature power spectrum is, right? But there are limits on the amplitude of it. So yeah, we assume just a flat spectrum, but below, whatever the current experimental limits are.
So usually we know the power, the height of power spectrum in large scale because we know the CMB,
Right.
but we don't know the small scale fluctuation, and we have to so.
Oh, right. The small scale.
We have to assume some shape of the power spectrum in the small scale if we want to make prediction.
Right. The amplitudes are slightly different, but the shapes are all flat.
Okay.
Yeah.
Flat and determined by the CMB power
Yeah.
spectrum. Okay.
oh, and my second question is, you mentioned about the gravitational wave signal, right? So can you distinguish this signal from the gravitational, gravitational wave background from the inflation?
No, well, I mean, there's two parts to the gravitational wave signal. One is actually from your first order phase transition, which we kind of neglected here, right? It would be an additional contribution. The inflationary contribution comes from your curvature power spectrum.
Okay.
So using the values of the curvature power spectrum in that flat spectrum, we get a certain gravitational wave signal. So it is the inflationary. It is the inflationary.
Oh, I see. Not
Yeah.
from the phase transition.
Right. We're saying the same power spectrum that can create the right PBH density that we want
Oh, I see.
also generates the gravitational wave signal that's interesting.
So what's the order of gravitational wave for the phase transition compared to this induced gravitational wave?
That's a hard question. So for the phase transition, it would really depend on how strong your phase transition were. If you had a very weak first order phase transition, you can have practically no gravitational waves. If you had a very violent, very strong first order phase transition, then of course you would get a very strong signal.
Yeah, because this kind of gravitational wave is always there, right?
Yeah.
Even if in your calculation you eliminate such a signal, but it's always there. So
Yeah.
the true signal is actually the summation of this Q kind of gravitational wave. And you just feed the parameter by induced gravitational wave to get the parameter that you want, right?
Right. Yeah.
So I'm wondering if the gravitational wave from the phase transition is higher than this kind of induced gravitational wave, then the parameter.
Oh, right. No, you're right. So yeah, so it would really depend on the strength of your phase transition. But again, that depends too much on our PNGL model. So we could probably compute some estimates. And you're right. So it could be either that these induced gravitational waves that always come from your curvature spectrum, they could be the dominant ones shown here, or you could have actually a peak due to your first order phase transition. That's also possible. Yeah. The peaks, by the way, if you had such a transition, would correspond roughly to each of these each of these points. So for our PBH dark matter, the first order phase transition signal would have a frequency around here. The strength is very uncertain.
Any other question? If not, let's thank you again. Thank you very much for the next talk.